Hi everybody, welcome back to Chem 121. I don't know what's going on anymore. It's week 5. That's about all I know. Let me wind this down real quick. There's a cat here. Hi, do you want to say hi to the class? Say hi, Maya. Say hi. Maya. 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 Oh, she's too busy. She's too busy rubbing against the chair arm. Oh, now she wants to talk. Well, it's too late. What do we got going on this week? So there's a lot going on for week 5. Traditionally for any class, really, because this is around when midterms start happening, and that's not any different for our class. We do have a midterm. It will be on Friday, and it'll be open all day. Very important. This is in the syllabus. I'm going to send out an announcement about it later today, too. If you cannot take the final on Friday, if you cannot take the midterm on Friday for whatever reason, doesn't matter. It could just be like, hey, I need an extra day because I'm really busy this week. Or maybe you have like another midterm on that day or something, whatever. Send me an email. If you don't send me a message, I'm going to assume that Friday is okay. If you cannot do Friday, I can move your exam to either Thursday or Saturday. And I can just type that into Canvas. I can't go further past Saturday because then I get to the point where I'm withholding people's scores until I have all the exams in, and then people are going to be waiting on that. So, let me know if you need me to move the date for you specifically. You do have to make that request over email. So if you do it right now, obviously all this text is going to go away when I close the window. In the chat log over here. So make sure that you send me an email about that or ask in Discord. I prefer email just so I have a log of like, okay, I did this. Just so I don't miss anything. What else do we have? So quiz number 3 is due tonight. It closes tomorrow, so you have 24 hours past the deadline tonight to turn it in for last call. And then quiz number 4 and lab worksheet number 2 are both due tomorrow, and those close Wednesday. My strategy for success here would be to do these early. Don't push them off because you will want to have taken those quizzes so that you have an idea of what material will be on the exams and can better prepare for it with an extra day. So that's my earnest advice for people who are like, what do I do for studying? The last thing that I would recommend is that if you go into the modules page, so let me get that on the screen real quick here. There we go. Oh, what are you guys doing? They're like fighting. My cats are arguing. Right here, there we go. So let me make sure that shows up on the page. Yeah, okay. So if you're in the modules tab and you go to this link right here, there is a study guide for the first exam. And if you click on it, it has a list of all the topics that we have covered. So if you aren't sure if you have covered everything that you need to, if this ever loads, like, holy crap, this is going real slow. Let me just hit refresh here. Oops, hold on, I lost all the windows. There we go, okay. And so, if you, let me make this bigger here. If you look through this document, it will tell you everything that will be on the first exam. So you should be able to do all these things. And if you can, you're in good shape. And if you're not able to do some of these things, you have a few days to prepare. So there is that. Okay. Chapter 5 is on the exam, so we need to actually get this done with so that we can have some basic understanding of the topics that I'm going to test you on. So I do need my tablet for this, so I gotta get that. Oh, excuse me. Oh, I swallowed my water funny, sorry. Ugh, sorry, I didn't mean to cough into the mic there and I couldn't mute it in time. Alright, so Chapter 5. Chapter 5 has to do with covalent compounds. Just like Chapter 4 was ionic compounds and everything involved with them, Chapter 5 is going to be covalent compounds and everything involved with them. Oh, just a second, I need to drink more water. Okay, I think that might be better. The first thing that we're going to have to learn how to do is how do we draw a Lewis structure for a covalent compound, because the rules for these are going to share some things in common, but they're not going to be exactly the same. Because, as we discussed in the previous chapter, ionic compounds form when we move electrons around and we create charges. But covalent compounds don't have charges at all. So we're going to have some different effects here that are going to be relevant. Now, the idea that covalent compounds were a thing that existed came about when various chemists and scientists observed the chemical and physical properties of these compounds. Ionic compounds were very common and well studied, but covalent compounds initially were confusing. In fact, for the longest time, people thought water must be an element on the periodic table. In fact, that idea goes all the way back to the BC ages, where people, particularly like the Greek philosophers, thought that all of the elements of the world came from the four primordial elements: fire, water, earth, and air. Yes, this is actually a thing. This is not Final Fantasy. This is where elements in video games come from, is ancient philosophy. And for a long time, water, being as stable as it is, people thought there's no way that water isn't an element on the periodic table. But it turns out water is a compound of hydrogen and oxygen. And people thought that it was elemental because it's so stable. The melting point of water is below room temperature. In fact, if you go outside today, well, maybe not today, it might be a little warmer than that, you would encounter a temperature at which water would actually consider being a solid. For most other substances, you have to heat up the ionic compound or whatever solid is in question to hundreds, if not thousands of degrees Celsius before it even considers becoming a liquid. But water will just do this at 0. And that's unusual. Most substances aren't like that. Most substances have high melting points. Other examples of things that have a low melting point are things like gasoline. Gasoline is a liquid at room temperature, and it actually needs to be cooled down even further before you get solid gasoline, which seems really weird. Like, you go to the fuel pump and it pumps out a solid. Like, that would be strange, right? There are other examples that exist, such as things like acetone, like oxygen that you breathe. Those, for example, are all very low melting point substances. Now, another feature of covalent compounds is that if you have them in the solid state and you hit them, what you end up with is just like a crumbly powdered mess. So, for example, if you have sugar and you put it in, like, say, like a grinder, or maybe you even like grind it up using a mortar and pestle, what you end up with is this extremely fine, chalky kind of powder. As opposed to if you do this with salt, you get a very fine salt, but it's still very granular. So ionic compounds are granular. They're still crystalline. But covalent compounds as solids are not crystalline at all if you grind them up. They are very, very fine. I have another cat here now who... I fed you guys, so go away. I'm just going to give him the elbow. Now, the conclusion that people drew when they saw these different properties of these different compounds was, oh, okay, the bonding in covalent compounds must be different. There's no way it can be the same. Otherwise, they would observe very, very high melting points and everything would be crystalline. So our job in this chapter is going to be, let's figure out how the bonding actually operates by drawing a Lewis structure, and then we can start comparing differences and stuff. Now, all atoms follow the same sort of goal when it comes to bonding. I want a full octet. This is just the thing that atoms want to do. So our objective in following the octet rule, exactly the same. Get 8 electrons. If we can do that, then we're in good shape. Now, covalent compounds don't have the option to transfer electrons to get to the octet. And here's why. Let's suppose that I wanted to make a fluorine compound. And oops, I should have drawn that correctly, but that's okay. 1, 2, 3, 4, 5, 6, 7. There we go. Fluorine is in group 17 and has 7 valence electrons. And if I'm going to transfer electrons from one atom to another, then this one would have 8 valence electrons, and that'd be all right. But this one would get further away. So by just transferring stuff and creating an ionic bond, I end up in this sort of impossible situation. If I move an electron, somebody will get an octet at the expense of the other thing, which is now farther away from getting an octet. And there's no way that I can shuffle these around. I just don't have enough electrons, right? So, an ionic bond with 2 nonmetals can't possibly work. I really screwed that writing up. There we go. Can't possibly work because there's no mathematical way to get both people to have octets when you just have 14 total electrons. You'd need to have 16 total, right? And I can't even add another fluorine into the mix here. If I had a third fluorine, then I'd be depriving that one of an electron too, and everyone would just be upset. So we have to do something different here. And so the result that we get forms a covalent bond. And what we're going to do that is, instead of transferring an electron and making 2 ions, we're going to share electrons. What the heck does that mean? Sharing electrons just means that, hey, I have electrons, you have electrons, we're both really close to getting an octet. How about we just both use this one? And that'll count for each of us. So let's look at what that means in a picture. So we're going to look at fluorine again, and here it is. I've drawn it as a picture this time. And what I'm going to do is, first of all, I'm going to slide them closer to each other like this. There you go. And you'll notice that I have arranged them in such a way that their unpaired electrons are now paired together. Sort of, right? So here are the electrons that are being paired, quote unquote. And what we can now do is the following. The electrons that I've highlighted in yellow are my shared electrons. And if I check for octets, I observe that this fluorine has 8 electrons, which is an octet. And then if I check for octets over here, notice what I'm doing. This fluorine has 8 electrons, which is also an octet. I forgot the minus sign on my electron. There we go. So by double counting our electrons, we end up in a situation where the result is both atoms think that they have an octet. Now, atoms are dumb. They don't have brains. So they think this is fine. But the result of this is that these two atoms are now stuck together. And so wherever one of these fluorine atoms goes, the other one has to go too, because otherwise it'd be making off with its electrons, right? Hey, those are mine. So these are now bonded together. And the bond that is formed is called a covalent bond. So the covalent bond is these two electrons in the middle here. And we'll indicate that with the pen here. So this is the covalent bond. Now, what about these other electrons on the outside here? All of these pairs are called non-bonding electron pairs. And what that means is that they are not participating in bonding. Only the covalent bonded electrons participate in bonding. So covalent means sharing electrons, and ionic is swapping electrons. That's correct. Now, not really swapping, but more donating or transferring. Because swapping would mean I give you something, you give me something. And then we end up where we started. Ionic is more, I have extra electrons that I don't want. You need electrons. Here, take mine. But yeah, you're on the right track there. Now, instead of drawing a bunch of dots between two atoms, which can get really confusing when we make multiple bonds, what we're instead going to do is we're going to draw this as a line. So the electrons that are used in bonding, the shorthand notation is that we draw this line here. And so each line represents two bonded electrons. So whenever you draw a line, that is intending to represent two electrons that are shared. So both atoms have access to the electrons in the line, in the bond. All the other electrons that are non-bonding are just attached to whatever atom it is that they're attached to, and they only count towards that atom. But the electrons in the bond count for both that are along the bond. All right, so you now know how to draw a Lewis structure using shared electrons. Now, some other important caveats here are that when we are drawing each of the bonds for our covalent compounds that we're going to make, we've already said that each line counts as two electrons. There's really only one way to do this when you're connecting two things together. And that is, I'm going to use some generic atoms here. I'm going to have atom A and then atom B. In order for me to make, I'll just put some other electrons around it here. In order to make a bond that consists of two electrons, I have to connect the unpaired electrons. So the unpaired electrons get shared to form the bond. So I can't share pairs of electrons because I have to put them between the two atoms. And for the pairs, there's nowhere for two electrons to fit in with other electrons. So for example, if I had this, which had 8 electrons, and then this fluorine here, which had 7, and I tried to make a bond, I can't share both of my electrons because this one's going to be like, huh? There's no space here. There's only room. So I would not form this bond. I can't have a pair of 3. I can only have a pair of 2. Can covalent bonds have metals like ionic compounds, or are covalents always nonmetals? So the problem with forming covalent bonds and metals is that the easy way for them to get away from or get to an octet is for them to get rid of electrons. So that's what they end up doing. So for instance, if I have sodium and fluorine here, so here's what fluorine has got, and here's sodium. If I wanted sodium to get to an octet, I'd have to share 7 electrons with it, and that's way too many electrons. So it's very easy for me to just pass this one over to form this, right? And so this would be ionic. And so metals, because they have so few electrons, don't really want to do covalent bonds because they can't get to an octet anyway by adding electrons. They have to get rid of their electrons. So it's just by virtue of how many electrons they have that dictates the type of bonding that we observe. So metals almost universally do not participate in covalent bonding. They want to ditch their electrons. They want to form ionic bonds. For nonmetals have lots of valence electrons again. And the only way for them to get to an octet is for them to share. So this would be covalent. So yeah, covalent will, for our purposes, always be nonmetals. All right, the next thing that we care about is that when we are looking around atoms, again, each line counts as 2 electrons, and the total number of electrons around the atom should be 8. That counts bonds too. So if you draw a molecule and you have your lines there for bonds and whatever, and you circle an atom, passing through a bond counts as 2. Oh, let me say that again. I was looking at OBS when the upload cut out. Passing through a bond when counting electrons around an atom counts as 2 electrons. Yeah, my internet cuts out like every hour because Comcast is shit. So I apologize. Now, not all atoms follow the octet rule. Particularly, the most common exception is hydrogen. Hydrogen is too tiny to have an octet of electrons, so it follows just a helium's sort of configuration. It just wants 2 electrons. If you form a bond to hydrogen, it's content with that. All right, so with that in mind, let's do some more examples of drawing Lewis structures here. So I'm going to do the first one. Oops, I thought there was homework practice there. And then you can go ahead and do the other ones. So let's draw chlorine. Chlorine is in group 7. It's going to have, group 17. It's going to have 7 valence electrons. We're going to make another bond to another chlorine. And you're going to look at this and be like, wow, this is exactly the same thing that we just did with fluorine. And yeah, totally it is, because they're in the same group, yeah? So what I'm going to do is I'm going to pair the electrons together that are unpaired. So I'm going to pair these two together. And I'm going to form a covalent bond. And that's going to look like this. And then the remaining electrons I just draw around the outside as non-bonding electrons, because that's how they were initially, right? All right, so whenever you form a covalent bond, you're going to form it between the single electrons on each atom. Now, in this case over here, for CF4, if I draw carbon, you're going to notice, oh, they're all unpaired electrons. So how many bonds can I make? Well, draw out your fluorines and see if you can determine the answer. And draw a structure for it. And you're going to see that these structures get quite big at times, and we're going to be drawing them fairly large. So I'm going to give you about 3 or 4 minutes to try and draw these out. Obviously, there's no way you can draw this in the chat unless you're like some sort of ASCII font wizard or something like that. Don't try to do that. Just let me know when you're done. We'll go over the answers in just a moment. So see you in a bit. All right, one more minute. We'll go over the answers together. All right, let's go over the answers here. So let me selectively erase these. And oops, I didn't want to erase those. Well, now I'm just going to erase everything. We'll just quickly redraw Cl2 on this thing. All right, so what we're going to do is, let me just draw Cl2 on here again so you have it. So I got to select the paintbrush, don't I? All right, so let's look at BRF. So here's bromine. Bromine's also in group 7. So it has 7 electrons. Sorry, group 17. I'm thinking of 7A here. And then, oops, I want fluorine here. Also in group 17, so it has 7 valence electrons. We're going to pair these 2 electrons together. And so I'll make my covalent bond the blue line here. And so this is what your molecule should look like. Now, if all this was good for was bonding halogens together, it'd be kind of a silly thing, right? But we can bond any nonmetals together at all as long as we can attain octets by sharing electrons. And so what we're going to do is we're going to take a bunch of fluorines here. So I'm going to go like this. So I've got 1 fluorine here. And then this is faster than me drawing them over and over and over. So we're going to go copy, paste, paste, paste. There we go. Now, what I need to do here is I need to share all of the the unpaired electrons. So, like, I could share this one and this one. And I could share these 2. And I could share these 2. And then I could share these 2. But this is not a Lewis structure. And the reason for that is because bonds are always in straight lines. So what I've drawn here is sort of like a football diagram. So I need to tidy up. And so that's what we're going to do. So we're going to tidy up. And the result that we will get will look like this. So I had carbon bonded to 4 fluorines, which I'm going to draw like that. And each of those had 3 pairs of non-bonding electrons, which I'm going to draw in afterward. And this is what your structure should have looked like when you drew it on paper. Now, does it matter if you make it a plus versus like an X where I tilt it like 45 degrees in either direction? No, it doesn't matter. Should all my bonds be at right angles? We're actually going to find out later on in this chapter that no, that shouldn't be the case. But for now, this is fine. All right, let's do water, the last one. Oh, why did that happen? Hold on, let me see here. I think I understand what went on here. What does that combination of keys do? I now see why something is happening when I do that. Because I hit a button and it makes everything grayscale. Does my pen still work? No, I can't even draw on the map anymore. Undo brush tool. Redo brush tool. Sorry, hold on. Alt Control Z. Oh. Okay. Yeah, so I gotta do this. I gotta open it again. That's okay. You can pause the video and go back and see that if you need to. Okay, but hitting that combination of keys apparently like screws up my Photoshop. Good to know. Oxygen is in group 16, so it has 6 valence electrons. Hydrogen is in group 1 and has 1 valence electron. All right, how do I give everyone an octet? Well, first of all, hydrogen doesn't need an octet. It just needs to pair with something, and it will be fine. So the initial idea would be, oh, I'm just going to do this and this, right? And then we'll tidy up. There's my oxygen, and then there's my hydrogen. Excuse me. So if you're drawing all your bonds at right angles, that's a great way to get started. Later on, we're going to try and draw our bonds with more respect toward what the molecule actually looks like, as opposed to this shorthand. Because right now we're drawing all of our molecules as flat entities on paper. Molecules aren't flat, or else we would all be like Paper Mario. You'd turn sideways and you'd completely disappear because you're two-dimensional. And molecules aren't like that. So we need to accommodate that by drawing them as accurately as possible, and we'll deal with that later on. For now, this is good enough. All right. Any questions on drawing covalent compounds, let me know. That's the basics of drawing a covalent molecule. Just connect the unpaired electrons. Now, that strategy that we just applied to just connect the dots there doesn't really work for molecules that get more and more complicated. We're going to see that in this next section right here. All right, so I'm going to give you simple molecules that are allowed to form multiple bonds. And in these cases, it's going to be very obvious, like, oh, I'll just connect all the unpaired electrons like we did before. But I'm going to have more than one electron get shared. So for instance, if I'm looking at oxygen, which looks like this, and I take 2 of those oxygen atoms and I put them together, and I say, well, I want to form covalent bonds. How can I do this with oxygen? And the answer is, well, if I take these 2 and I link them together, and then I take these 2 and link them together, and then I go like this, I have a frog. It doesn't look very good on the screen, though. That's okay. No, I don't have a frog. What I do have, though, is a molecule where all of the electrons can be shared within the molecule, and I just need to make 2 lines, right? So if I pair these 2 sets together, the result that I get is this. And remember, each pair of shared electrons is a line, so I'm just going to draw 2 lines. So this is how we make a double bond. I'm going to just share 2 pairs of electrons between 2 atoms. I could do a triple bond and share 3 pairs of electrons if I wanted to as well. We're going to show that on the next screen, and then we'll talk about what happens if you try and share 4, because that'd be perfect, right? I just put 2 things together and have them share all their electrons, and then everyone's happy, right? Well, we'll see if that works out. So if you want to make a double bond, you just share 2 pairs of electrons between 2 atoms. Let's look at nitrogen. I'm going to draw nitrogen like this with 5 valence electrons. I'm going to have another nitrogen here with its 5 valence electrons. Can I get everything to have an octet? Well, let's share my electrons. So I'm going to share these 2. And I'm going to share these 2. And I'm going to share these 2. And what's the end result when I am done with that? I get N with 3 shared pairs of electrons. And I have the non-bonding pairs on the outside. And there we go. Now, something I just remembered that we should probably be doing is we should be checking for octets, right? And so we can go back to any of these molecules that we've drawn so far and check for octets. So what I'm going to do is I'm going to take a different color, and I'm going to go like this. I'm going to circle an atom. And what I want to do is I want to check to make sure that it has 8 electrons being shared with it. So if I count each of these electrons as 1, 1, 2, and each of these lines is 2, because each line is 2 electrons, 3, 4, 5, 6, 7, 8, I have 8 electrons. And the other nitrogen over here would too. So this satisfies the octet rule, and the structure must be good. What about if I go back to, say... Well, you do that with oxygen here. So I'm going to circle in oxygen. And then I'm going to count the electrons. 1, 2, 3, 4, 5, 6, 7, 8. So this one's good. Same for the other oxygen. What if I went to this diagram here that we drew for water earlier, and I circle this oxygen, like that, and I count electrons. 1, 2, 3, 4, 5, 6, 7, 8. So it follows the octet rule as well. So this is a good check to make sure that you are drawing the structure correctly. Is circle any atom and then count electrons. All the individual electrons that you drew as dots are 1, and each of the lines is 2. And then, of course, always remember that hydrogen doesn't care about the octet rule. It just needs to have any bond, and it's fine. All right. This one I want you to try to do real quick, because I think the homework practice is after that. Yeah. So what I want you to do is I want you to try and draw these 2 molecules, C2H2 and C2H4. And my hint is that you want to have the same number of H's on each side for each molecule. So, in other words, on C2H2, don't put both the H's on one C and then ignore the other C. So, you should have something that looks kind of like this for C2H2, but you're going to have to figure out how to connect the dots. So draw in all the dots and then figure out, okay, what electrons do I have to share? And then for C2H4, you would do something like that, and you'd have to figure out how to connect the dots. So go ahead and draw those, and I want you to tell me which one is a double bond and which one is a triple bond in the chat once you've got the answer. I'm going to give you about 4 minutes to do this, and we'll go over the answers in just a bit. All right, one more minute. We'll go over the answers here. All right, let's go over the answer. So we'll go back over to here. And so I'm going to draw each of these out first. Like this, and then I'm going to put in the electrons around them. And so the first thing that we should probably do is just connect these guys, right? That's straightforward. I kind of missed there. Let me try that again. There we go. And then I'll just connect the other pairs. And then we'll tidy up. Ah, I messed that up. Hold on. And that's my structure. And I can check for octets, so hydrogen doesn't count, but I can check this carbon by circling it and going 1, 2, 3, 4, 5, 6, 7, 8. Everything has an octet. Everything is great. Now we'll do the other one over here. H, C, H, C, H. H, that's not really a dot. Let's fix that. There we go. And then we'll connect the H's again. We'll just put them wherever. It doesn't matter. And then what that leaves me with is to do these. And then we'll tidy up. And there you go. So C2H2 had a triple bond, and C2H4 had a double bond. And you can observe that from the structure, but it's kind of hard to predict that based on the formula. Generally speaking, the more atoms that you have, the fewer double or triple bonds you need to make. And so if I were to have even more hydrogens in here, I would only end up with a single bond. And so on and so forth. Now, when we come back from the break, we're going to take our 10-minute break here. What we're going to do is we're going to explore a more rigorous way to draw Lewis structures. So this connects the dots idea is fine, I guess, but it's not going to work for really complex molecules where I have to have double bonds and triple bonds at various different places. So we're going to need to come up with a better methodology, which we'll do after the break. So I will see you in about 10 minutes for that. So go grab some water, and we'll be back in just a bit. Hi everybody, I'm back. Anybody have a cat who, no matter how you brush them, it just seems like you can never brush all their hair? Like it's just an endless amount of fur? That's kind of how I feel like Maya is, because every time she jumps up on my lap, I'm like, oh, okay, I'll brush you. Like, I actually have the cat brush here now at my desk. And she's starting to enjoy it, but what I'm noticing is that no matter how much I brush her, it never seems to end. And now I have like a garbage can full of hair, and she's not that large of a cat, so I'm concerned. A lot of screaming. Yeah, my cats do that too. One in particular, he came up and like yowled in my ear, and I don't know if the mic picked him up, but all right. So what we're going to do for this next section is we are going to describe a way to draw the Lewis structure for any molecule that you can think of. And so this is going to be the method that I recommend that you use over connect the dots, because connect the dots, while it does work, may lead you down a lot of wrong paths before you get to the correct answer. So I show you guys to do that connect the dots method just to show you the general idea of how Lewis structures are formed. What we're going to do now is we're going to pivot towards this new method, which is a little bit more complex, but it virtually assures that if you follow the steps in the right order, you will end up on the correct answer. All right. So we're going to call this the 5-step plan for drawing the Lewis structure for any molecule. And so we're going to apply this whatever we can to any Lewis structure that we see from now on. So why can't H2O, H gives up an electron and oxygen donates 2? And then we balance it out like we did in ionic. The reason that that doesn't happen is that because hydrogen, for the most part, is also trying to get to an octet. And by octet, what I mean is a duet or 2. And if I give away my electron like this to make that, then I don't get closer to having 2 valence electrons. So hydrogen's a nonmetal, so it's not going to give up its electron. It wants to accept an electron as well so that it can attain its duet. So we don't observe hydrogen just giving up electrons in these types of compounds. Now, I'm saying that because it follows the model that we're going to talk about. Later on in Chapter 10, what we're going to learn is that hydrogen totally does that. However, there is a caveat to it, like both hydrogens wouldn't do it. Only one of them does that. For a very specific reason. It has to do with acidity and basicity and pH, which we'll talk about in Unit 10 when we talk about acids and bases. So, you actually have a good idea, but for neutral water, water follows a covalent blueprint because it's made of nonmetals. All right, let's talk about our 5-step plan. So whenever we draw a Lewis structure, we're going to follow these 5 steps. Now, very important, these 5 steps must be done in order. And if you cannot do a step, you skip it and you don't look back. What do I mean by you can't do a step? What I mean is there's nothing for you to do when you get to that step, so you just go to the next one. Okay. All right, so here we go. Step number 1, you're going to count the valence electrons in all of our atoms. So remember how I said that if I had 2 atoms with their electron clouds and they bonked into each other, only the electrons on the outside would interact, right? So only the valence electrons will form bonds. And the core electrons hang out. So when we get to drawing a Lewis structure, we are only going to count valence electrons. What that means is that you're going to go to your periodic table, you're going to find what group an atom is in, and then count the number of valence electrons, and that one will contribute. So, for example, if I had CO2, which is the example we're going to do in a little bit here, and I wanted to count valence electrons, well, carbon is in group 14 and has 4 valence electrons. Oxygen's in group 16 and has 6 valence electrons, and there are 2 of them. So what that would mean is that in CO2, there would be 16 electrons available for bonding. So when I draw my Lewis structure of CO2, it should have 16 electrons in it, because those are the 16 electrons in the valence layers that are available for bonding. All right. Step 2, draw some sort of framework that helps you connect all of your atoms together. We're going to ignore the octet rule until the very end, basically. And we're just going to sort of scaffold this together. So, for instance, if I had this molecule written right here, H can't go in the middle, but I could do something like this as my scaffold. So this is what I call the framework. Other textbooks or other instructors might call it a skeleton. I call it a framework or a scaffold. If I was doing this polyatomic ion over here, my scaffold would be something like this, where I connect the O's to my carbon. Notice that nothing has an octet yet. That's okay, it's just a scaffold, right? It's only the framework. We haven't finished. We're just connecting all the pieces. Now, if I do this, I have to use the electrons that I counted up here, right? And those electrons are going to be used to make bonds. So this would use... the pen got away from me there. This would use 4 electrons for the 2 bonds. Whereas over here, these bonds over here would use 6 electrons for 3 bonds. And we would deduct those from the pool of electrons that we counted in step 1. Now, how do you know what goes in the middle? The best hint for what goes in the middle is the first element in the formula goes in the center of the structure, with one exception. You can't put H in the middle. Hydrogen can never be a central atom because it can only form one bond. So therefore it is always consigned to the outside. But whatever your formula is, whatever element comes first is going to be your central atom. So long as it's not H. And that's how you draw your structure. So put the thing that's supposed to go in the center, put everything else around it, connect the lines to it, deduct electrons. The next few questions are going to be in relation to your framework. So we're going to spend the remaining electrons doing these things in this order. Step 3, you're going to put electrons around atoms that are bonded to the central atom. So what this means is that you want to give outer octets first. So the outer atoms get octets. We're going to do an example of the whole thing, so I'm just going to go through the remaining steps here. Step 4 is if you have leftover electrons, they go on the central atom. And then step 5, if you run out of electrons for the central atom and you don't have an octet everywhere, then and only then do you make multiple bonds. The final important caveat for following these 5 steps is that if at any point every atom in your structure has an octet, stop what you're doing, and put the pencil down, your structure is complete. If everything has an octet, exception is hydrogen. Hydrogen only needs 2 electrons. You have the Lewis structure for your molecule, and you don't need to do any of the remaining steps because there would be nothing to do anyway. Another caveat to that, though, is you do have to use all of the electrons. If you make a mistake in your structure and then say, oh, I have octets for everything, and then stop, but you didn't use up all the electrons, or you used too many, you have the wrong structure. So be very careful. Whenever people tell me, hey, is my structure right? The first thing I do is I count their electrons. Or if somebody asks me, hey, I got stuck drawing this, what's wrong? And I say, well, you don't have enough electrons, right? You're supposed to have 12, but you only drew 10 there. And then they go, oh, yeah. And then immediately they fix the problem. So the hardest part of this process, believe it or not, is counting. Can you count to the number that you wrote down earlier in terms of its number of electrons? And it turns out that most of us can't. I sure can. I make mistakes like this all the time. So I'll sit there and be like, why is my Lewis structure not working? Oh, because 7 plus 5 is not 10. Like that sort of thing, right? We can't do basic addition. So double check your addition and your counting, because that's what's going to screw you up. The rest of the steps are pretty straightforward once you've done this enough. So you'll be okay. All right, so we're going to do the Lewis structure for CO2. What I'm going to do, though, first is I'm going to go over here. Oops, that doesn't help me. And instead of my slides walking us through it, I'm going to just draw it out for you. I feel like it's easier to follow if you can actually see the structure being drawn in front of you. So we're going to have to do all 5 steps in order. So the first step was count valence electrons. And so we need to do that. So we're going to work over here. And we're going to draw the Lewis structure for our CO2. Now, we have already counted the valence electrons in a little example that I said earlier. So we said carbon was in group 14, has 4 valence electrons. Oxygen is in group 16, it has 6 valence electrons. And there are 2 oxygens. And so 4 plus 2 times 6 is 16. In step 2, you're going to draw the framework of the molecule. C is my central atom, so I'm going to put carbon in the middle, and I'm going to put the oxygens around it. You can put these wherever you want to. I'm going to put them across from each other, and the reason why we do that will be explained in the next section. Or maybe on Tuesday. I don't know if we'll have enough time today. I'm going to then connect everything together for my scaffolding. Now, when I've done this, this uses 4 electrons. So here's 2 electrons right here, and here's 2 electrons here. So 4 electrons were used. And so that means that the total number of electrons that are left is 12. So I've used 4 of my 16 electrons in my diagram. All right, the third step, we're going to fill in the octets for the outer atoms. So if my structure looks like this at this point, I need to fill in octets. Now, you just draw them in here. You don't need to do one at a time here because you're just going to give something an octet. So 1, 2, 3, 4, 5, 6. That would be an octet for that atom by doing that. Because if I circled it, I would go 1, 2, 3, 4, 5, 6 for the dots I just drew. And the line counts as 2. So there's our octet. I got to do the same thing over here. All right. I drew 12 dots. So of the 12 electrons that I had left right there, I used all of them. Step 4 is any leftover electrons that we have should go on the central atom. It turns out that I don't have any leftover electrons, so we're just going to have to skip step 4. That should say needed, not heated. There we go. Step 5 is multiple bonds wherever we need them. So if we go up here and I check for octets, let me just draw the structure that we have so far. This is our structure following this plan. And so if I look for octets, I would say, well, this carbon does not have an octet. It only has 4 electrons around it, 2 from this line and 2 from this line. It needs to have 8 electrons. So what I'm going to do is I'm going to take electrons that are not paired and I'm going to shove them into a bond. So I'm going to take the electrons off the outside. I'm going to like this. Whoop. All right, they're no longer non-bonding. They are now bonding. So I'm going to promote them to bonding. These 2 electrons are no longer non-bonding. I'm going to promote them to bonding. And I'm going to keep doing that until everything has an octet. Because now if I check the octet, I have 4 bonds connected to my carbon. That's 8 valence electrons around it. It now has an octet. I can then check the octets of other atoms on the side here. So I have 1, 2, 3, 4 valence electrons plus 4 from 2 lines is 8. And the other oxygen would be good too. So everything has an octet. And the result that you get is the structure of the molecule. That's a lot of steps, but as you do this process over and over and over, it gets significantly easier. So your job is going to be to follow the steps in order and apply them to structures. So let's walk through what we just did again over here. We're going to count valence electrons. We're going to draw the framework, which I drew on the screen. We're going to put electrons between the atoms to start our framework. That was 4 electrons total so far. I don't draw them as lines here just because I'm showing where they are as electrons. Step 3 is to do octets on the outer elements. There they are. That's all 16 electrons. We've run out of electrons, so we have nothing to put on the central atom for step 4. Step 5 is to make multiple bonds, which we're going to do this, and there you go. All right, now that you've seen me do it, I want you to try and do it. I'm going to give you ammonia, and I want you to draw the Lewis structure for this. So, write out NH3. You're going to need a periodic table so you can count valence electrons. And do the 5-step plan. Step 1, count the electrons. Step 2, draw a scaffold framework. Step 3, outer octets. Step 4, inner octets. Step 5, multiple bonds as needed. I'll give you 3 or 4 minutes to try it. We'll go over the answers in just a bit. See you soon. All right, one more minute. We'll go over the answers here. All right, let's go over the answers here. So step number 1 is to count valence electrons. Our nitrogen has 5 because it's in group 15. Our hydrogen has 1 because it's in group 1, and there are 3. So we should work with 8 valence electrons total in our structure. So I'm going to draw something like that, and then I'm going to connect them. 1, 2, 3 lines. 3 times 2 is 6 electrons. So I have 2 electrons that are left over. Then I would do outer octets, but they're all hydrogen on the outside, so I don't need to add any electrons to any hydrogens. Then I would put the remaining electrons on the central atom to complete its octet. So I've used all the electrons. Does everything have an octet? Hydrogen only needs 2 electrons. Nitrogen wants an octet. It does have an octet. I do not need to make multiple bonds. My structure is complete. It should look like that, and it turns out it totally did. All right, excellent. So now that you've seen this in action, I'm going to give you a bunch of molecules, and I want you to try these for them. Now, there are some effects that we do want to consider for specifically ions. If I was going to count the number of electrons in NH4, I would do it like this. So here's a nitrogen. Here's my hydrogens. So I have 5 plus 1 times 4 equals 9. But then I'm going to do this to it. What does this mean? How do you get a positive charge on something? Well, you do that by removing an electron. So if you see a positive charge on your ion, that's how many fewer electrons you have to work with. Likewise, for something that's an anion, so chlorine would be 7 valence electrons, oxygen would be 6, and then this minus is an extra electron. So if you see ions, don't panic. All that's telling you is, hey, you have a different number of electrons than you would if it was neutral. Okay? Otherwise, the rules are exactly the same. So go ahead and draw the Lewis structure for these 5 5 molecules or ions, whichever ones you are doing. This is going to take you a bit of time because you need to go through all the steps. So I'm going to give you like 6 or 7 minutes. And then we'll go over the answers, and then that'll be it for today. So go ahead and try these, and we'll go over the answers in just a little bit. Let me know if you need help. I am in the chat. Happy to help you in whatever way I can. So see you in a bit. All right, one more minute. We'll go over the answers here. All right, so what we'll do is I'll just do this. And we'll just move this over a little bit. Actually, let me just do this too. There we go. All right, so I'm going to do these fairly quickly. I'm not going to write out the steps 1, 2, 3, 4, 5 each time, but we will do them in the correct order. So for CS2, carbon has 4 electrons and sulfur has 6, and there are 2 sulfur. So let's draw our framework. I'm going to put the carbon in the middle and the sulfur on the outside. 2, 4 electrons. So 12 left. We'll do octets on the outside. 7, 8, 9, 10, 11, 12. That's all the electrons I have. But I don't have an octet yet, so I'm going to... There's nothing I can do to put on the central atom because I don't have any electrons left. So I'm going to take 2 electrons here and do this. And I'm going to take 2 electrons here and do that. And there's the structure. And we're all set. All right, for CH2O, carbon is 4, hydrogen is 1, and there's 2 of them. Oxygen is 6. So total electrons would be 4 plus 2 plus 6 is 12. I'm going to do the same thing I did before. Carbon goes in the middle. I'm going to just put everything else around the outside. Connect, connect, connect. So that's 6. I'm going to put octets around this one to use the remaining 6. I don't have anything left to put on the oxygen in the center, so I can't... Or I'm sorry, the carbon in the center, so I can't fill that one. But I can make a double bond by doing this. And there you go. There's the structure. So hopefully that's what you got. Next we've got ammonium, which is 5 electrons plus 4, oops, that's the wrong order. Sorry, hold on. Each hydrogen is 1, but there are 4 of them. And then this positive charge means I'm removing an electron. So the total number of valence electrons should be 8. And it turns out that this Lewis structure is incredibly easy to draw. Because I only have 8 electrons, I just do this. 1, 2, 3, 4. Now, and there you go, that's the structure. Now, something that you do with ions, because you want to indicate the charge on here, and you don't want to put it on any specific atom because that would make it look like it's ionic for a bond. The convention is that we put brackets around it. We put the charge in the top right corner like that. So if you didn't do that, that's totally fine. But that's what we will do from now on for anything that's a structure that is also a polyatomic ion. Then we got PCl3. So phosphorus is in group 15, that's 5 valence electrons. Chlorine is in group 17, that's 7 valence electrons. And there are 3 chlorine. So we have 26 electrons to play with here. So I'm going to go like this. Connect, connect, connect. So that's 6. And then I'm going to do octets. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I did 6 dots plus the 2 that are already there from that line. That gives me my octets there. The remaining 2 electrons must go on the central atom. And I have no need to draw anything else because everything is an octet. So there's our structure for PCl3. And then finally for ClO minus, chlorine gives you 7 valence electrons, it's in group 17. Oxygen gives you 6 valence electrons, it's in group 16. This minus gives you an extra electron. So there are 14 electrons to play with. That's going to use 2 to do that. And then I just go 2, 4, 6, 8, 10, 12. I should have done the oxygen first before I did the chlorine because the oxygen was the outer atom. But that's okay. Oops. That's not what I meant to do. And there you go. So there's the structure for that one too. All right, so that's how we draw Lewis structures for complex molecules in covalent compounds. Make sure that you are doing the homework practice on these because there's a lot of various problems that are good practice. So I would definitely recommend doing them in preparation for the quiz for Unit 5 and also the exam that's on Friday. I'll talk a little bit about the quiz on Tuesday after we finish the chapter, because we should finish this tomorrow. But that's all that we have for today. I do want to thank everybody for coming out to the lecture. And let me know if you have any questions at all. Sorry, I'm trying to find something. There we go. Let me know if you have any questions at all. Midterms are coming up, so this is the time for you to be asking me questions about the material. Please do that either by email or in the Discord channel. And then make sure that you get quiz number 3 in by tonight and quiz number 4 and lab worksheet number 2 by tomorrow. It's a busy week. Stay on top of it, and then after Friday, take the weekend off. That's how we're going to work things here. All right. Thanks for watching, and again, let me know if you have any questions in the Discord or by email. Take care.